When you look at a city skyline, you just assume it's all solid, right? We trust that the buildings we live and work in are safe. But what if I told you that sometimes the biggest dangers are designed right into them, that they're hiding in plain sight? Today, we're going to pull back the curtain on a hidden architectural flaw that has led to absolute catastrophe. All right, let's get right into it. Take a good look at this building. I bet you've seen 100 just like it. It's your standard apartment block, and hey, it's even got that convenient open parking on the ground floor. It looks totally normal. But the most dangerous thing about this building is also the most common thing about it.
So the weakness isn't some hidden crack or a bad batch of concrete. No, it's the design itself. It's that open ground floor. And to really get why that's so incredibly dangerous, we first have to understand what happens to a building when the very ground it's standing on decides to shake, rattle, and roll.
See, every single building is in a constant fight with two completely different forces. One of them is simple and predictable. The other? It's pure chaos. And knowing the difference is quite literally a matter of life and death. Okay, so check this out. Buildings are geniuses when it comes to gravity, right? Weed is simple. It just wants to go straight down, following a nice clean path right to the foundation. Easy. But earthquakes, they don't play by those rules. They don't push down, they shove violently from the side. And all that chaotic energy has to go somewhere. It has to be absorbed by the entire building. If that path to the ground is broken, that energy will hunt down the weakest spot it can find. And that weak spot, it has a name. It's called a vertical irregularity. Basically, it's any sudden, jarring change in the building as you go up. Imagine you have a bunch of floors with heavy brick walls, and then, suddenly, they're sitting on top of a wide-open ground floor with just a few skinny columns. That abrupt change, well, that's the whole problem. This is the perfect way to think about it. Picture a heavy-duty steel chain. Solid, right? Now, what if we replaced just one of those steel links with a flimsy plastic zip tie? If you yank on that chain, where is it going to break? It's not going to be the steel. It's going to be that one plastic link every single time. An earthquake does the exact same thing to a building. It finds that one weak link and unleashes all of its destructive force right there. And this isn't just some engineering theory, We've seen the absolutely tragic results of these hidden flaws again and again. So let's break down the specific types of irregularities that can turn a normal-looking building into a total death trap. The most common, and by far the deadliest, is something called the soft story. And this brings us right back to our apartment building with the open still parking. You've got this heavy, rigid box of upper floors sitting on top of thin, flexible columns. It's like a heavyweight boxer trying to stand on a pair of spindly ankles. As soon as the shaking starts, where do you think all that movement is going to go? Straight to the ankles. And that leads directly to a horrifying event called a pancake collapse. Those ground floor columns are forced to bend and sway way beyond what they can handle, and they just buckle. The entire building above them drops one full level, crushing everything and everyone on the ground floor. This exact thing happened with devastating consequences during the 2001 Bhuj earthquake in India. Just to give you an idea of this scale, in the city of Ahmedabad, which was hundreds of kilometers away from the earthquake's epicenter, more than 100 multi-story buildings collapsed. And guess what? Nearly every single one of them had that exact same soft story design flaw. Okay, on to the next type. Another one you see all the time is a geometric irregularity. This is when the building's shape suddenly changes. Like when a wide base suddenly steps back to a much narrower tower, maybe to create a nice terrace or a penthouse with a view. Well, that nice view creates a huge problem because it interrupts the smooth flow of those earthquake forces. There was a hotel in the 2015 Nepal earthquake with this exact design, and it suffered incredible damage. That notch where the thin tower met the wide base, it acted like a trap. It concentrated all the stress into one tiny area and literally pulverized the concrete. The building didn't completely pancake, but the damage was so bad it was a total write-off. Now this next one is really wild because it feels so wrong. It's called a floating column. This is when a column that's holding up the upper floors just stops. It doesn't go all the way to the ground. Instead, its massive load gets shifted sideways onto a huge beam, usually to create a big, open, column-free space below, like a hotel lobby or a ballroom. So here's the deal. This design breaks the #1 rule of earthquake engineering, which is to have a clear, direct path for forces to get to the ground. Instead, the earthquake's energy travels down that column and slams into a dead end. It has no choice but to take a violent 90-degree turn and shoot through a beam that was never, ever meant to handle that kind of lateral stress. If that beam fails, the whole section of the building above it just comes crashing down. So, after all these disasters, the evidence just became impossible to ignore. For decades, the approach was to kind of manage these flaws, to design around them. But a huge shift in thinking was on the horizon, one that was about to completely rewrite the rule book for building safety. Yeah, the old philosophy was basically to accept the bad design from the architect and then try to make it work. An engineer would just add more steel or make the columns a little bigger. They were essentially trying to put a stronger patch on that weak link instead of just getting rid of the weak link altogether.
But then came a revolutionary update to India's seismic code, the one for 2025. And it takes a completely new and frankly much smarter stance. It says, we are done trying to compensate for a fundamentally bad idea. The new philosophy is simple, it's powerful, and it's this: eliminate the problem before it even starts.
And there it is. The new code flat out prohibits the construction of soft stories in most of the country's high-risk and populated seismic zones. This isn't a guideline. It's not a suggestion. It's a ban. That open stilt parking design, the one that caused so much devastation, it's now illegal to build in most places where it matters. And this ban is just one part of a much smarter set of rules. Instead of just slapping a patch on the problem, the new code demands way more sophisticated computer analysis to actually design these flaws out from the very beginning. And in the rare cases where a soft story is absolutely unavoidable in a low-risk zone, the new limits on how much it can flex are so incredibly strict that they basically remove the weakness anyway. So, with these incredibly dangerous flaws now banned, how do we move forward? Well, the new rulebook doesn't just tell us what not to do. It actually points us toward a future of much smarter and much safer building design.
You know, the best practices all start way before anyone even thinks about pouring concrete. It starts with the very first sketch on a napkin. The idea is to keep the building's shape simple and regular. If you absolutely have to have a complex shape, then you break it up into simpler blocks separated by a small gap. The key is avoiding those sudden, abrupt changes and, maybe most importantly, making sure the architect and the engineer are in the same room, working together from day one to design the danger out.
And really, this is the main takeaway. This is the core message of this whole thing. You simply cannot fix a fundamentally flawed idea with more complicated math and a little more steel. A safe building is a building that was conceived the right way from the very start. So the next time you're walking down the street and you look up at a building, ask yourself this: does it look like a single, unified structure where every part is working together like a team? Or can you spot those abrupt changes? Can you see the weak links that an earthquake will someday find? Because a building that's built to survive is one that works together, with no single part ever left to take all the strain alone.